Hello and welcome to another one of these ADD videos. Today we're going to be looking at ionic equations. Water itself is a very poor conductor of electricity. However, when we put ionic solutes in water, these ionic compounds will dissolve readily in water due to its polar nature. Now, some ionic solutes will dissolve more than others depending on their solubility. But as a result, the ones that do dissolve will have the dissociation of their ions, meaning that that ionic compound that's dissolving will enter the water as separate ions. And we're going to assume 100% dissociation for the amount that did dissolve for the ionic compounds. Okay? So again, solubility strength will dictate the electrolytic strength. So electrolytes, again, are the solutes that we dissolve to yield these ions in the aqueous solutions of water. The strong electrolytes are good conductors of electricity and very soluble in water, whereas weak electrolytes are poor conductors of electricity and not so soluble. So that's what this is explaining here. It says that this occurs when a compound has a low solubility in water and only partly dissolved in water. So you don't have as much ions as you would with something that's more soluble. The amount that does dissolve has 100% dissociation, and there aren't as many ions for the ones with lower solubility. Therefore, they're not as good conductors of electricity and weak electrolytes. So typical dissociation equations look at the solute becoming the individual ions. In a saline solution, when you put salt into water, like in an IV drip, you start out with the solid crystals of salt that become the individual ions. AQ is used to indicate that they're surrounded by water, which is referred to as hydrated. So make sure the elements are balanced. If we dissociate this beryllium chloride, we need to put a 2 coefficient in front of this chlorine. Also, polyatomic ions need to remain intact. So you see how the PO4 stayed PO4. A molecular equation is a chemical equation in which the ions are written together and it's not very descriptive. Ionic reactions, whenever we combine two ionic solutions, we can have the ions in some situations will remain as ions, but other scenarios will encounter the supersaturation effect that leads to low solubility and precipitation formation. If you don't know what I'm saying there, go back and look at the basic solution video. So what happens is you will get ionic interaction with some of the ions, and the ions then form a precipitate, a solid, whereas the other ions just basically watch the whole thing occur because they don't interact. Ionic equations are chemical equations in which the strong electrolytes are written in dissociated form with their charges. Alright, so now if we were to look at this example here, it might make a little bit more sense. Here we have lead acetate added to sodium iodide to give us the solid of lead iodide, and this is sodium acetate. So this is a molecular equation. If you study it carefully, you'll notice it's not balanced. Here we have one iodine and two iodines. Here we have one sodium that's balanced. The leads are balanced, but the acetate ions are not. So to balance the equation, we need to add some coefficients. These two 2's right there. So now the sodium ions are balanced as well as the iodide, but this is still molecular. This is not descriptive. This is not showing you what's interacting to get all this and what's canceling out. So to get a little bit more descriptive, we can convert to an ionic equation. And an ionic equation has anything that has an aqueous or an AQ after it separated into their ions. And in this process, you'll have to convert any subscripts into coefficients when in ion form. 2NaI becomes 2Na plus 1, 2I minus 1. Same thing would occur for this sodium acetate on this side. All right? So in order to be good at this, you have to know your charges and formulas for these ions. So go back and review that if you didn't get it the first time around. So now let's look at this ionic equation. We have the lead acetate separated into lead 2 plus, and then because of this subscript of the 2, we have a 2 coefficient for the acetate ion. Notice I'm still putting the AQ afterwards. And then here, we went through that part already. The solid remains together because it's a solid. And now you should be able to see that there are these things called spectator ions. These are ions that do not take place in the reaction. So you see that there will be an opportunity to cancel some ions. Okay? So there's 2 acetates that can go by on each side. And then there's, let's see, 2 sodium ions. These are all spectator ions. And then we need the iodide ions. We need the lead ions. So that's it. So you'll always be canceling out your spectator ions. So once you cancel out your spectator ions, you're left with the net ionic equation. All right? So that was a lot of information to digest, so make sure you understand it well. Check out another example video, and most importantly, practice, practice, practice. Thank you and have a nice day.